Good morning, good afternoon, everyone. Welcome to Keysight Technologies virtual event series. We are pleased to have you here for today's virtual event on accelerating your speed to test with the state-of-the-art advanced signal integrity tools. My name is Girish Baliga from Keysight Marketing, and I am the moderator and presenter at today's webinar. Today, we will be spending the next 45 minutes or so deep diving into accelerating your speed to test with state-of-the-art advanced signal integrity test tools. Before we get started, couple of housekeeping inputs. During the presentation, you can dial in your questions in the Q&A box on the streaming console. We'll be more than happy to answer your questions and get back. Also, please share your recommendations on the survey form, which will appear as a pop-up during the course of the webinar. There is also resource collateral on accelerating your speed to test with the state-of-the-art advanced signal integrity test tools on the webinar console. You can download these from the resource list. In addition, please share your comments about the program as well, enabling us to serve you better. And please use audio headset or earphones to listen to the virtual event audio for good audio effect. Like I mentioned earlier, I will be presenting today's paper on accelerating your speed to test with the state-of-the-art advanced signal integrity test tools. Just a brief background, I manage the marketing for wireline, 5G wireless, aerospace defense, and software at Keysight Technologies. Without much ado, let us begin the session. Understanding jitter and decomposition techniques are paramount to understand and ensure that one speeds the test with respect to advanced signal integrity test tools. As you can see in this slide, we will get started with a basic introduction to jitter, a review of various jitter decomposition methods, advanced jitter analysis with the crosstalk removal tools, and then talk about scope random jitter removal from jitter analysis in the next few slides. Jitter is a word which is associated with the instability. The definition of jitter by electronic engineers is something like this. A simple definition would be a jitter is the time difference between when a predefined event should have occurred and when actually did it occur. The time difference is expressed in unit interval or UI, and 1 UI is the value of the bit period of the ideal clock signal. This time difference can be treated as phase modulation. In other words, jitter is the short-term phase variation of the significant instance of a digital signal from their ideal positions in time. Jitter can also be defined as the deviation from the ideal timing of an event, and the reference is the differential zero crossing for electrical signals and the nominal receiver threshold power level for optical systems. So now let us understand, where does jitter come from. Sources of jitter can be broken down into three primary contributors consisting of the transmitter, the physical media, and the receiver. The perspective of transmitters and receivers will depend on the user's measurement reference point. As we see, random jitter or Gaussian can usually be tracked as a source or a transmitter problem. Random jitter can often be the most difficult jitter component to track down, primarily because it is not correlated with the data signal. Duty cycle distortion, or DCT, is another jitter component that is usually considered a transmitter source problem. Periodic jitter, or PJ, as you see from the slide, can either be uncorrelated or correlated and can be viewed as either being generated by the transmitter circuit or PJ can be coupled into the transmission line. Whether this source of jitter is correlated or uncorrelated, it is ultimately synchronous to something. Therefore, if one is able to trigger on the various suspect sources, one may be able to eventually track down the source. Intersymbol interference or ISI jitter is usually a component of jitter in high-speed data signals. The primary culprits of ISI jitter include limited bandwidth of the transmitter, limited bandwidth of the data media, specifically the transmission line, as well as termination problems at the receiver side or impedance discontinuity within the physical media. Now let's take a closer look at some of these individual jitter components and how they theoretically look and are revealed with the jitter analysis. So at the top of the diagram, you see a clock reference. The clock reference can be generated from the clock recovery module, and then that clock reference is compared to the source waveform in the transition. And this is where one is able to see jitter if the transition appears earlier than the reference transition. Then one will have a negative error in terms of a time interval error. So when a transition appears later, one will have a positive error. So what we do in the time interval error plot or the TIE plot is we plot that particular error versus time. So if one looks at the bottom of the time interval error plot, and if the signal appears earlier, then like we said earlier, it will have a negative error. And if the transition happens later, then we will have a positive error. And the collection of all these errors are called as the time interval errors. This will be used a lot in this particular slide set, and we will correlate to that when we use it to do jitter decomposition. What is real-time jitter analysis? The various types of timing measurements can be viewed in different formats. The most common view for repetitive jitter measurements has traditionally been the eye diagram, where the scope is triggered with a real hardware clock and the NRZ data is captured repetitively with an infinite persistence display mode to visually show the worst case timing and voltage variations. An eye mask opening can then be applied to this type of display to test for compliance to a specific specification. For debugging and time correlating specific timing errors back to the data or clock signal, the trend view can be a very powerful display tool to find the sources of real-time jitter. The trend view plots successive timing measurement results on the vertical axis with the horizontal axis linked to the oscilloscope's time base. In other words, it's time versus time. So during the course of the presentation, we'll spend much more time discussing how the TIE trend waveform can be interpreted relative to the NRZ data signals for specific components of jitter. Other useful views of plotting the real-time measurement results that can provide additional insight into source of jitter includes histograms, spectrum displays, bathtub curves, etc. How do real-time oscilloscopes measure jitter? A real-time oscilloscope first acquires a record of the signal, in this case a NRZ serial data stream. Next, the embedded clock is recovered using software. The clock recovery is always required for performing a series of time interval error jitter measurements. Other jitter measurements such as cycle to cycle clock jitter, N cycle jitter, as well as parametric measurements do not require clock recovery. Next, the timing error of each edge of the signal relative to the ideal recovered clock can be plotted as a jitter trend waveform. The vertical axis is plotted as the time interval, in this case the TIE, with the horizontal axis plotted as running time. And this is synchronized to the oscilloscope's time-based axis of the acquired waveform. This type of display is extremely useful for time correlating jitter to the original data signal or to other signals that may be coupling in and causing jitter. In addition, math functions such as averaging can be used to manipulate the jitter trend view in order to eliminate and or isolate specific jitter components. The spectrum of the jitter is determined by performing the FFT on the jitter trend data and then plotting the results as timing error on the vertical axis versus frequency on the horizontal axis. That is the time error versus frequency. The spectrum view can be very useful for identifying deterministic jitter components as well as the uncorrelated period jitter. Finally, the traditional histogram of the jitter is provided showing the statistical probability distribution function or the PDF of the jitter. Histograms are always plotted as time error versus n or the number of hits. With the repetitive acquisitions, the histogram view will continue to build up statistical data for more accurate results. The next thing we would like to deliberate is about the jitter components like I mentioned earlier. Why is it important for us to separate the jitter for analysis? The main reason by having all the different jitter component separated, one can figure out where the source of the problem is coming from. Let's look at what the jitter components are made out of. On the top right, you will see the total jitter where we sum all the jitters together. This is the total jitter, but they can also be grouped into two main categories. On the left side, one can see the bounded category. It means the jitter are introduced by these components are limited, so these don't increase over time. So we see that one is the deterministic jitter, and this particular deterministic jitter or DJ can be separated into different categories. One where it is correlated with the data or the data dependent jitter, and underneath it are the two main subcategories, the duty cycle distortion or DCT, and this is mainly due to the difference in the rise and fall time. So one when one is having a different rise and fall time, the pulse width is going to change on the positive and negative pulse, and that is where it would cause duty cycle distortion. And another subcategory is the intersymbol interference, and this is mainly caused by the limited bandwidth in the channel. And one once has a limited bandwidth, it will cause the ISI, and that is dependent on the pattern. So the longer runs of zeros or ones that one has is going to affect very differently from the pattern in the waveform. And now the other subcategories of DJ is what we call the uncorrelated with data. So this has nothing to do with the data pattern, and the other term we call is the budge or the bounded uncorrelated jitter. And this can be further subcategorized into two different categories. One is the non-period, and this is mainly due to the crosstalk when one has a non-repeating event or a one-time event coupled into the signal, and that causes a budge or a aperiodic bounded uncorrelated jitter. It's fairly long, but a budge is what we would usually reference it to. The other subcategory under the BUJ is the periodic jitter, and this is mainly caused by clocks in the system. So, if one has a high-speed clocking system and that's coupled into the high-speed signal, we refer to that as the PJ or the periodic jitter. So all these components we are talking about are bounded, so it doesn't increase over time. But if as we keep moving towards the right hand side, that is highly unbounded, and this jitter characteristics is very different than what I described earlier. This jitter here is called as the random jitter or RJ, and they basically increase this over time. again, it's very important to know where the source of the jitter is coming from so that one can identify what is the root cause of jitter and help fix in the design. So let's go through an overview of how jitter decomposition is done. So when a oscilloscope acquires a waveform at the top right, then it tries to recover the clock from it and then generates the reference clock. There are many ways to generate the clock. For example, it can use a first order PLL or a second order PLL, or there are many such ways to get there. But generating a reference clock is important because after that, one uses the reference clock to evaluate the time interval error or TIE. Once the TIE is computed, then one does further analysis with it. The first step is to do the data dependent jitter analysis. So then all the data dependent jitter is removed from the TIE, and what is left is the DRJ and the PJ TIE records. Then the next step would be to extract the RJ from the RJ and PJTIE record so that one can separate what component is random and what component is periodic. Once this step is done, then the next step is to perform dual Dirac analysis, and it is where one can compute the different values of the jitter components that make up and report the total jitter, the random jitter, and the dual, and the deterministic jitter from the signal. So, from a high level, this is how the jitter decomposition works. Therefore, depending on the role of the resource who would make the measurements, there are four critical areas which one needs to be aware of. The first one is waveform acquisition, where it's not just acquiring the waveform, but also what goes on in the front of the oscilloscope, the signal fidelity in the connection and the oscilloscope settings, which we will discuss in further detail. The second is about the clock reference selection area, which is a direct clock or a phase lock loop or an estimated CW clock. Then we do have the DDJ area or the data dependent jitter area, which includes the pattern type and the length expected. And then finally, we have the RJ extraction methodology, which talks about the actual algorithm which is used for RJ estimation. If one gets any of these wrong, then it will be a compromise on their measurements. Let's go after these one at a time. So, though we have understood a bit about what this means, what we need to understand here is the scope doesn't know what you have in front of your device as far as it concerns the signal that it's at. It's the input is the signal you want it to measure, and if one's got some bad probing or a bad fixture or bad cables which are not taken care of or deskewed, then if there is any poor match anywhere in the system, it's going to affect the result. So typically, one of the most important part is to ensure that the system which has been used is going to be kind of spick and span with respect to having the right type of device with the right type of probing and the right type of fixture and the cables which are kind of taken care of or and are of much better quality. The next important aspect here is the oscilloscope settings. Once you have the oscilloscope scale setting, the threshold setting, the hysteresis and acquisition lens, and we'll deal this separately on how these needs to be considered. Now let us understand more about the clock reference part. The clock reference, like I mentioned earlier, is always to have a clock as a reference for jitter measurement. It can be a number of things, whether it is externally available or probably previous edges on a signal, or often it can be either a constant clock or it can be a software PLL like it is on real-time oscilloscopes. So that's pretty much where we are going to dwell at this point. So let's understand more about the clock reference. Moving on to pattern types, one of the key concerns would be to ensure that the algorithms for jitter measurements are very effective with respect to periodic patterns. There's also a caveat here that is that we need to capture multiple repetitions of a pattern so that we can take advantage of averaging. For example, we would like to take, say, 500 repetitions of a pattern so as to be able to do certain things. For patterns that are really long, like say 2 to 31, we need to go to in what is called as the arbitrary mode. And the recommendation here is to use a shortened pattern if possible to appraise the quality of the link, then switch to longer patterns or random data with arbitrary mode. So one is using a larger pattern, they need to evaluate what the channel is doing to the data, which mostly and where the ISI is coming from. If one does not know what that is, then one does not have a pattern, so one loses information. So in effect, one needs to find that information from by doing regression and also doing edge to edge influencing of the data, and it's algorithmically less efficient than the period, but it's certainly doable, and it definitely works. And the dual direct assumption is a very common way to do jitter decomposition, and it is based on this premise. So once we compute the RG right from the signal, then one tries to fit the RJ Gaussian curve to the tail of the TI histogram. So as you can see from the graph here, that's the TI histogram, and since we know what the RJ component is and how and what are the characteristics, so one tries to fit it to the tail end of the histogram. So if one looks at the rate curve right to the left and the right hand side of the tail, then one knows how to fit the RJ into the histogram. And once one has made the fit, then they would be able to compute the total jitter. And the total jitter is basically reported as a peak to peak to a target bit error rate number. So the equation you see here is the summation of the dual direct of the deterministic jitter plus a number of factors called by n and then multiplied by the RJ RMS. So the n, as one may know, is not really fixed. It really depends on what the target bit error rate is. And for example, at 10 to the power of minus 12, the n is about 14. So as the ER increases, the n is also going to get bigger. But if one can remember, random jitter increases over time. So one accumulates more and more bits. There would be more randomness in the jitter, and the n will increase over time. So typically at the 10 to the power minus 12, n is about 14. So one can apply those components in there and calculate what the total jitter P to peak is for a target BER number. So we talk about the dual Dirac as an algorithm to estimate the total jitter, but there are two main underlying methods for doing the jitter decomposition, and they are the spectral and tail fit. They really define how a random jitter expression is done. So let's look at in more rational for using those methods. Spectral has existed for many years, say probably more than a decade or more, and because of that, there's a lot of steady and a lot of consistency right through the past measurement. It's why spectral is being used here, and spectral is also accurate for low crosstalk conditions. So when there is very little crosstalk, it can really estimate jitter very accurately. The fairly new method being introduced in the last few years is called the tail fit. It's a general purpose and it's really accurate in high crosstalk conditions. So really depending on whether one has a signal or a crosstalk, they can pick up different methods and the expression methods for jitter separation. So now let's jump into a spectral method a little bit deeper and understand how the RJ extraction is done. Remember, right in that flow, once we have the TIE records, one removes the data dependent jitter from the histogram. So what is left is the PJ and RJ spectral content. And that is what we are seeing at the top of the graph. The spectral content contains the periodic jitter and also the random jitter at the bottom. What one does after this is to apply the PJ threshold to separate what component is PJ and what component is random. The PJ threshold is really chosen by experimentation. So once there's a lot of study which is done, and this is basically chosen through experimentation. And once there is an application of the PJ threshold, then it would be some of these PJ components which would become the PJ RMS, and what's left behind is being integrated to derive the RJ RMS. So this is pretty much how the spectral method. So in the oscilloscope, there are a lot of graphs that would show how jitter separation works. And as you see, this is one of those graphs which actually show the RJ-PJ threshold and then where one applies the separation threshold. So it's actually shown in the green color line in the first graph, and that's a fairly simple problem. We see the spikes in the spectral and then apply a separation threshold, and everything above in pink, that's basically the PJ summit of what's left at the bottom, that's the RJ. So it's that pretty simple. But is that really simple in the real world? And the answer is no. Because in the real world, the RJ may not be that flat. So if one looks at the bottom graph, one can come into a situation where there can be a big lump of a signal, and then the question asked is that lumped RJ or PJ, are they specifically random or periodic? So what does one specifically do in such? This is where there's a feature on the scope that can help the designer make a better separation of the jitter decomposition. So as we see on the left side, as seen in the previous graph, we can apply a linear and flat PJ threshold through a wide RJ bandwidth analysis. In the scope, there's a feature where one can pick between a wide or narrow RJ bandwidth, and once one picks wide, then they apply a linear or flat PJ threshold. So once basically it's above the PJ threshold, it's going to sum up as PJ. But as you can look at the result below, that first graph, the RJ is about 1 picoseconds, and then there's a big PJ number, another 3 picoseconds. Now, one also has to have the other method called the narrow RJ bandwidth analysis. That is where one does not apply a straight PJ threshold. So one has a non-linear PJ threshold that tracks with the waveform. So what one is seeing here is a highly alias spectral, and then what one does is apply a separation threshold in green that's non-linear. So one can see a very different number right below the graph. The RJ now increases significantly from 1 to about 9 picoseconds, and the PJ drops from 93 to around 27 picoseconds. Now the question is which PJ threshold and RJ bandwidth analysis do one choose from? We have the ability, but how do you know what one to use for which jitter separation? This is where the above top curve will come in very handy. So again, we have the wide and narrow RJ bandwidth comparison side by side. And what one wants to go is to look at the above top curve in the screen below. So let me explain a little bit more about the above top curve and what it is. The above top curve basically extrapolates the measured data to what the TJ should be. So the blue color is what we have actually acquired from the waveform, and then the white color curve is what we extrapolate to. On the left side, on the wide RJ bandwidth configuration, one can see that there is a kink on the extrapolation. So it's not smooth, and there is a big discontinuity, and that tells that something is not right. So if one looks at the right hand side where the setting is the jitter decomposition to narrow, one has a smooth transition from the measured to the extrapolation. So the right side is actually the narrow RJ configuration, which is more accurately reporting the actual TJ than the left side, so which is under reporting the TJ. So this is a very important graph, and a lot of designers use it a lot. Basically, the smoothness of the slope continuity is really critical. The smoother the curve, the more accurately the extrapolation works for one's measurement. And there is also a setting only very specific vendors like Keysight offers both wide and narrow. So this helps evaluate which method is best suited for the user's signal and for their designs. So spectrum method has been working really well for many years, but recently with crosstalk affecting the signal more profoundly, one finds that the spectral method does not handle the presence of crosstalk very well. So as you see in the previous slide, there's a discontinuity issue. Instead of cutting in, it's actually curving outwards into the above top. So as it's highlighted in the circle, in the dotted yellow circle, as you can see it, there's something wrong here, that one doesn't have the very smooth continuity, and the yellow dotted line is showing that what the slope continuity should look like, and should get extrapolated correctly. Therefore, obviously something is not right here, and because it comes in really fast in the wide slope, the algorithm is basically overestimating the RJ severely. So even though the signal is not performing as bad, but it's showing it's pretty bad using the spectral methods. So let's now spend a little bit more time about the crosstalk and how crosstalk can affect the signal. When on the left side you see you have a victim rising edge, it's pretty clean, but once you have the cursor, crosstalk can couple into the victim, and it can change the shape of the edge. And this is where the crosstalk can affect the jitter measurement and slope discontinuity. And the other way to look at the crosstalk issue is the Gaussian of the RJ or PJ histogram. So in effect, without the crosstalk, it looks pretty Gaussian, but as soon as one has crosstalk coupled into the signal, it becomes non-Gaussian. So that's an indicator of crosstalk being present in the signal. So this is where the tail fit method can really be useful, and the tail fit is somewhat similar to the dual Dirac, but it's not exactly the same. And it performs a Gaussian fit to the left and right of the RGPG histogram, but it does an additional step. It actually goes out and looks at a low probability event out in the tail to see if there's any crosstalk that's present there. So this is the difference between the tail fit and also the dual Dirac, and the tail fit actually applies a Gaussian fit even without the knowledge of the RJ, and thus will look out in the tail to find the one time or the crosstalk event. To show the tail fit algorithm actually is performing what it should be, we did something for the experimentation with the presence of the crosstalk. If you look at the left hand side of the slide, we have a situation where we have no crosstalk, and the spectral and tail fit extraction would yield the same result, about 1.7 picoseconds. But with the presence of crosstalk on the right hand side, one can see that the spectral expression blows up. The RG increases from 1.7 to 6.15 picoseconds. So it's not accurately estimating the jitter of the system. But once we apply the tail fit extraction, that number drops and pretty much aligns with the situation of the no crosstalk condition. So it's been proven the tail fit can work really well with the presence of crosstalk. So again, the bathtub plot is really critical here, and look at how smooth the bathtub is, and it will be able to tell the designer if something is not working correctly or not right in the extrapolation. So the crosstalk tool can figure out which signal are being coupled on to the signal, and if one has uh, a clock, and if one is looking at a serial data aggressor, it can tell whether that is the signal which is causing a problem to the victim signal. It can also help quantify how much error and jitter each aggressor will add to the victim, so one knows how one can tackle and go about it. Then one can also remove the crosstalk for jitter analysis, what the signal would look like without crosstalk presence, and so on and so forth. And it can also help with the jitter margin and how it can be recovered without the crosstalk. And if the jitter spec was failing before, can it pass without the crosstalk? So all these are really aimed at helping the designer make important design decisions. So is it worth reducing crosstalk in the design, and where it should improve? And if it is clock that's causing the problem in the high speed signal, then where it should have better shielding between those signals is what the crosstalk tool can help. So Keysight Technologies has jitter analysis and crosstalk analysis tools that accessible to the designers through various modes. We do have the EasyJit Plus as well as EasyJit Complete for doing both jitter analysis and noise analysis. And depending on what kind of a mode, there are custom-made packages which the designers can choose, whether they want to customize the different clock recovery that matches their receiver, or any very specific different configurations. So we also have the PAM4 clock recovery package as well. So if one is interested in the crosstalk, we do have that too. For example, if somebody is talking about equalization, or somebody is talking about de-embedding, or one is looking at the BR counter, so all these tools will ensure that it will accelerate your speed to test with our state of the art advanced signal integrity test tools. Thank you, participants, for participating in today's virtual event. On behalf of Keysight Technologies, I would like to thank you all for taking time out and participating in today's virtual event. Like I mentioned earlier, please take time out to enter your requirements on the survey form, which will be shared to you at the end of this virtual event. Dear participants, we hope this session was helpful to you. This session would also be available on demand shortly, so that you can go through this virtual event again. On behalf of Keysight Technologies, we would like to thank you for participating in this session. As you may know, Keysight Technologies runs a series of virtual events periodically, and we'll keep you posted on the next set of virtual events over email and other modes. This virtual event will also be available on demand shortly, and you will get an email once it is ready at the address you would have used for registration. You can view this virtual event any number of times on demand. You can also share the on-demand details with your colleagues, team members, friends, etc., enabling them to register and participate. With that, we would like to sign off this virtual event. All of you have a nice day. Thank you and bye.